guys, welcome to the next lecture of IAS Scalars and Vectors. Today we have to do some concepts that are quite necessary for your IAS examinations. With that, we'll be covering some past paper questions so that our understanding can be reached at the top. First of all, let's assume that there is something that is basically having a mass of 500 kilograms. This something is balanced or attached by two forces. Both of them are T, and it's being balanced by that. Well, and they ask you in the question that they have given you the angles as well, 30 degrees, both of them are at 30 degrees, and they ask you to find the value of T. This is going to be one of the most important concepts that we have to do today in our lecture, and I'm going to be going really slow so that each and every point during the calculation you can understand and then apply it to all the concepts. First of all, you need to realize that there are two components of this tension. The first one is going to be the vertical component, and the second one is going to be the horizontal component that for now we don't need. But similarly, the second tension would also have these two components. One is going to be the vertical component and the second is going to be the horizontal component. We'll be doing this a little bit again in the forces chapter, but since we're doing vectors, we need to understand these two vertical components of the tension are actually balancing this weight. So these two vertical forces of the tension are actually balancing this weight. And then in order to solve this, you need to realize that there's a component of T. This is with the angle, so it would be called hypotenuse cos theta. So T cos theta plus this T cos theta, since both of these are acting upwards, is going to be balancing this weight. If an object is just hanging there, that means it is at rest, which means all forces are balanced. In this case scenario, you need to actually understand that this force, that component of tension plus this component of tension is actually balancing this weight, and that weight is going to be, since W is equals to mg, so it would be 500 times 9.81. So I would get 2t cos angle I have got, that's 30. Both of them has 30 angles, so the angle is going to be staying the same, or equals to 500 multiplied by 9.81. First of all, I'm going to be doing 500 multiplied by 9.81. Then I'm going to be dividing that by 2, and that again dividing it by cos 30. Just solve it up and you would get the value of tension, which would be around 2831, or tension will be 2830 newtons. Correct, to three significant figures. So this is how these questions can be asked in the examination regarding how to be solving the tension components. Today's lecture is solely based on this concept of balancing these forces. I'm going to be starting off without calculation. First of all, these, the magnitude with the vector diagram, not with the vector diagram. Vector diagram is going to be the next class topic. Mostly they ask about the vector diagrams. That's not going to be my headache for today. I'm just going to be solving it with this. Okay. Let's start off with this question. There is a question in front of you, Jan 2022, that the Tyrolean traverse is a technique, okay, for crossing the deep valley. The photograph shown the climber crossing the river, okay. The free body diagram of the climber is shown, all right. Okay, show that the tension T in the rope is this, okay. Now, if you need to realize that this weight is given as 650, and there are two tensions that are actually balancing that. I'm just gonna be making these arrows over here. They are basically in the center, but since I would make two in, well, like they would overlap, so it would not make much sense. So both of the arrows are basically in the center. Both of them are at the center, so just trying to making that. Okay. Now you need to realize that these tensions have two components. One is going to be this component, the vertical one, for both of the tensions, and the one is going to be the horizontal. We are not in like generally need horizontal component right now. Both of those horizontal component will be balancing each other out because it's in equilibrium. All forces are balanced. You need to realize that the downward force is 650. That would be equal to the upward force in this case scenario, which would be first of all T, that's T, and with the angle is cos 76 plus T cos 76. Now that becomes 650 is equal to 2T cos 76. So yep, so 650 first of all needs to be divided by cos 76, which would get you an answer of around 2686. Then you divide that by 2, you would get the value of T as 1343 or like 1343. You can round it off to 1.3 exponent 3 newtons. So this is something that you need to realize, okay, this is how you're actually solving these questions of how to be resolving the forces, equilibrium concepts. These are like generally very much asked in the examination. There's one more question before ending the lesson. A ball falls through a vertical height of 0.6 meters, bouncing at a point A. Show that the velocity of the ball immediately before the bounce is about 3 meters per second. Well, that's very simple. Since we are done with the motion equations, we can easily do that. Initial velocity will be 0. Acceleration will be around 9.81. And well, yeah, we have got the S, that's 0.60. So we'll use the Suvat equations. We need the value of V. So we can do V is equals to, or you can do S is equals to ut. No, we cannot do that. We can do V square minus U square equals to AS. Well, we need V square. The U is 0 equals to, acceleration is going to be 9.81, and then displacement is given as 0.6. So 2 times 9.81 times 0.6, you root the particular value, you get the value of velocity that is going to be around 3.4 meters per second. That's about that. Okay. Moving on. Now the question is that kinetic energy is conserved as the ball bounces off the ramp. The ball bounces at an angle of 70 to the horizontal. State an expression for the horizontal and vertical components. This is what one part that we need. So basically this is the bouncing of the ball. I'm just going to be like making it extended a little bit. Doesn't really matter. This would be the horizontal component and this would be the vertical component. You can either resolve them over here. If you want to resolve them with the angle 70, I've got no issues in that as well. So this would be the component, the vertical one, and this would be the horizontal one. Doesn't really matter, whatever you solve it. In downward, you have to subtract it from 90. Try doing this way. Okay. So now these are the components that I break. I'll just I would have to resolve them over here. I'll just resolve them over here just to make your concept very understanding. So if you were to realize that basically what happens is that this is the ball's velocity. When the ball hits the ground, it actually bounces back in this way. And then when it bounces this way, there will be two components. One is actually of the ball like moving to the right, and the other one is of the ball moving to the top. So this is how, like, this arrows basically represents once the ball has like changed its velocity value. Okay. This saying that kinetic energy of the ball is conserved. The ball bounces at an angle of 70 degrees to the to the vertical, 70 degrees to the vertical. And state an expression for the horizontal and vertical velocity components of the velocity of the ball immediately after the bounce. Well, immediately after the bounce, what would happen to the velocity of the ball? If the ball was hitting down with 3 meters per second and the kinetic energy is conserved, That means this velocity will be 3 meters per second. Now, this is very interesting, although I'm not very sure that you're very familiar with the concept of energy, but still, if kinetic energy is conserved, no, if the kinetic energy is conserved, assuming that this is not 3.3, it's like I will be using the actual value that I calculated, 3.43. So, kinetic energy is conserved, that means half mv square remains the same. So, velocity is to be conserved. Whenever they say kinetic energy of the ball is conserved, they actually mean that the velocity is conserved, not the component, the actual velocity value, because mass is not changing. Mass is constant for the ball. The mass cannot change. Na? Only thing that the kinetic energy is dependent upon, since kinetic energy is half mv squared. So only thing that the kinetic energy is like dependent upon is basically the velocity, because mass is already constant. So therefore, this velocity would be 3.43. And since I need this in this component, you can clearly observe that this is going to be the vertical component, that is with the angle. So with the angle will be 3.43 cos 70. Vertical one will be 3.43 cos 70. And the horizontal one will be 3.43 sin 70. This is a very good question, honestly. So 3.43 cos sin 70 first, and that the value will be 3.2. And cos 70, the value is going to be 1.2, 1.17, something like that. Okay, so this is going to be the answers for this. And on that note, I'm pretty sure that you understood the concept of how to solve these questions when there are forces acting at different points, and getting our answers. In the next lesson, we will be doing some scale diagrams and vector diagrams of how to solve these vector questions. And in those vector diagrams, we'll be covering a lot of concepts that are like important, and we'll be doing a couple of calculations as well. So stay tuned for the next lecture. Take care, guys. See you in the next lecture. Since you're enjoying the lectures, just wanted to inform you that there are premium batches going on. That is a direct way to get A's and A stars. It has got some exclusive content that is not generally available neither on the website nor on the YouTube. So you can join the batch to get your grade.